So my goals today is just make sure we kind of focus in on one aspect of what we talked on Wednesday, okay? So remember, Wednesday, I just went over some different perspectives, just making sure we're comfortable with some different derivative rules that we hadn't used in a while. But kind of introduced the idea that, these derivatives can help us describe functions, okay? So that was one of the reasons why I did some quick graphs to deal with and how we can help us here. Now, as far as the critical points are concerned, make sure you understand that if we're talking critical points, we're thinking first derivative. Okay. The critical points are going to help us whenever we think about a first derivative, because this is going to help us kind of find areas where a change in behavior can occur. So remember, the first derivative is a rate of change. So increasing or decreasing, those are kind of perspectives that we have. Well, a critical point is a possible location where that can change. Okay, and it comes from the first derivative. And now that I think about this function, I may not have picked a good function. Should still work. We'll see. So whenever, as I mentioned, as far as finding critical points, make sure you understand what that means is, hey, we're going to go in and take a first derivative. While I'm sitting here, I should be more careful picking my function. Let's change this one just to make sure it's not like yesterday's. I want it to be factorable. All right. Glad I thought about that before we jumped ahead. Okay. Don't want to have to do synthetic division. That's why I stopped before we jumped in that. Okay. Now, as far as the derivative, are we comfortable with the power rule when it comes to dealing with polynomials? Is there any concerns here where I'm getting this from? Everyone's good with that? Now, as mentioned, the critical points, this is where we're going to begin to step forward and say, hey, at what places can a change occur? All right, now there's different critical points that we focus on. One of those critical points is a horizontal tangent, right? Where do we have a slope of zero occurring when it comes to a rate of change. So one of the things that we do want to watch for is where f prime of x can equal zero. The other situation is not equal to zero, but where we get to that undefined situation. Right, this doesn't help us much because it's not going to be able to deal with anything. So remember, yes, our Wednesday, we looked at a vertical asymptote, right? A vertical asymptote would be another example of a critical point that we can use to help describe the function. We may not be able to plug in that number, right? Because ultimately what we're saying is x can't be whatever that value is. I should have put a, not x. Because it gives us a zero in the denominator. We don't want that, okay? That's something that can help us. A cusp will be another situation, right? Think of absolute value and that sharp turn it makes. That's another situation that, hey, it doesn't have a derivative equal to zero because we can't differentiate there. However, it's still something that's going to help us from a describing of the function standpoint. We're going to call it a critical point. All right. Now, as far as this one here is concerned, we're taking this function and we're setting it equal to zero to get to those critical points. Now, as I mentioned, I made sure this one can factor. What's one thing we can factor here that someone recognizes? All right, we can divide everything by 12, right? And I definitely encourage you, if you can divide out a common factor, make sure you do it. Since it's just 12, we can go through and divide as such. That way we just make it easier to work with, okay? Now, polynomial, I erased those other things. With polynomial, we're not going to have anything that's going to have a sharp term. There's no cusp that we're worried about here. There's no restricted values here. So that's why we're able to just focus on horizontal tangents, okay? What can I do here, though, for factoring purposes? What should we try anytime we have four terms? Yeah, this is where I would recommend jumping straight into some grouping, right? What do the first two have in common? What do the second two have in common? Now, I'm telling you it's going to work now, but like as we saw yesterday, this is not always guaranteed to work. Okay, not yesterday, sorry, Wednesday. Now just be careful here. I set this one up though to where that second group we have to divide out a negative. But oops. Once we get here, it's just determining whether these are the same or not. Okay, so hey, this time they are the same. We can definitely factor out that common factor. And we now have our polynomial in a factored form. So what would someone want to do next? All right, you definitely do jump straight in. If you wanted to, you continue factoring, but I feel like this is a little bit more straightforward to just set each of them equal to zero, right? Because here we could have just said, hey, that's x equal -1. I know we don't do it every day though. What do we have to be careful of with this one though? Yeah, make sure we get both solutions, right? So if you choose to do a square root, make sure you're acknowledging that by putting the plus or -2. In the end, when we look at our critical points, this will occur at x equal to -2, -1, and +2. So you'll see here, the whole difference was, hey, we had to take a first derivative and then set it equal to zero to get to these critical points. These critical points represent where we would have horizontal tangents of my original function. Okay. The slope is zero. Now, what we're going to find here, and as we saw with graphs, what we're also going to see is that means there's a change in behavior possibly. One side is increasing, the next side is decreasing, right? We'll kind of look at that with my last problem today, just kind of okay, what can we do with this? But is everyone comfortable with getting to this, what I'm asking for, critical points with this function? right? As far as the second function is concerned, all right, here's a rational for us. Now, one thing I would make sure that we're doing right away, anytime we have variables in the denominator, like we see here, make sure you go state your restriction. So like, hey, make sure I remember x cannot equal -1. So this is a situation where, hey, I have to be aware of this issue because this is actually probably going to be a critical point when I move forward. All right, so when I talk about critical points, -1 is going to be critical to what's going on with the graph. Well, based on what we talked about Wednesday, what we should be expecting is possibly an asymptote. Okay. Now, with that said, we can jump into our derivative here. So we're going to go through the quotient rule. So low D high minus high D low. Careful with your parentheses here. All over low squared. Now, I didn't write it up here, but when I say low, high D low, the derivative denominator is 1. So I didn't write it, but if you need to, make sure you put it there for your sake. Okay. Any concerns where I'm getting that from, though? All right. Now, here we know that we need to move forward with this, right? So this is a situation where I'm not just saying find and simplify the derivative. We need to use this derivative to find critical points. So we definitely need to simplify here. Okay. So we need to go through and multiply the numerator out. As far as this first one, remember x times 2x is where I'm getting my 2x squared from. 1 times 1 is where I'm getting the 1 from. Okay. All I did then for that 3x was, hey, what's these two terms give me? Nope, not those two, sorry. What do these two terms give me? And then what do these two terms give me? That's where the middle term 3x comes from. Okay. Continuing on with our simplification though, that'll give us what, x squared plus 2x all over x plus 1 squared. Now we know that we're going to be using this to find critical points. So here it's fully simplified, but what do you recognize about the numerator? What do they share in common? They both have an x. So I would encourage you to go one step. When you get here, just be like, hey, I know I'm probably going to need to do it, so let's just rewrite it. The big difference here is we're going further with this problem, right? Before we would have stopped there. No big deal. Okay, that was great. But now I'm asking you to identify critical points. Hey, let me make sure I factor that while I'm here, because that's going to make it a little bit easier for me. Okay. Any questions, concerns I could help someone with as far as getting to these? Going through this derivative, I should say. We're gonna have another example with exponentials, kind of bring it together, okay? So, but as we deal with this one here, remember now, hey, I have my derivative. We're gonna go try to find where we have critical points. So for this particular problem, we want to look at when is the derivative 0 and where is g of x undefined. Okay. Which hopefully you'll see here, the denominator, the factor in the denominator does not change from the beginning to the bottom, right? So that x equal to -1 is still a number we're going to be focused on, okay? Now make sure you understand here, when I say critical points, I'm not saying we can plug it into the function. We can't use -1, however, it's going to help us discuss like the increasing and decreasing nature of the function. Is everyone comfortable with how I got to that derivative though? I can erase that part. And make sure you see here first and foremost, as far as this undefined part, we already had that stated. I usually like to do that to deal with. So one of the critical points we're going to look at here is going to be the -1. The nice thing about using rational functions, I think we briefly talked about this yesterday, when you want to find where the derivative is 0, just use the numerator. You don't need the denominator. Setting the denominator equal to 0 will give us the very thing we've already found. Okay. So here, the nice thing about this is we find two more critical points, 0 and -2. So for this particular problem, when we say critical points, we need to make sure to highlight the fact that, hey, I'm going to look at 3 critical points this time. 0, -2, and then that -1. We're expecting a vertical asymptote here because we couldn't simplify the function. So -1 probably is going to be a vertical asymptote that both sides might have different things going on. Sometimes they could be the same, right? Once we start looking at different things, that'll help us, okay? Any concerns with where I'm getting this information from? I can help someone with? Yeah, so like if we're talking critical points, right? What we'd be saying is x equals -2, comma -1, comma 0. Okay, and I'm reordering them on purpose because we're gonna go look at the graph here and just kind of look at what that means, okay? Yes. Because these are not, we're not saying x-intercepts, we're not saying, zeros. What we're saying is, hey, these represent critical points of the graph. Critical points occur at these locations. Now, can we plug in 0 and -2 to our function? Yeah, we could definitely do that, right? So if we wanted to, we can go over here and say, hey, g of 0, well, that's going to be 1, right? G of -2, well, my guess that's gonna be -1, and that'd be 4. I was wrong. G of -2 is 4. My brain's not working. 3. Looks like it's 3. We'll see. Let's go look at the graph. Technology has not been my friend this week, y'all. Is that clear for everyone in the graph there? So as far as we were dealing with this, we said at g of x, sorry, not g of x, at x equal to 0, -1, and -2, we have critical points, okay? Now, as far as looking at this graph, the one thing that I hope we all agree upon is we can kind of see that vertical asymptote taking place there, okay? The other thing that we're going to see here is, why would I highlight these points out of all the other points on this graph? They're turning points, right? What do we know is true at those 2 points? Horizontal tangents, right? So we can go over here and we could find the equation of a tangent line at those points, and it's going to have a slope of 0. Okay. So those are 2 key points that we're focused on. Well, what you'll see here when we look at this graph, when we go through the derivative and we set the derivative equal to 0, these are the values that are being highlighted right there. Okay. Well, let's look at the graph. If I pick any point over here and I work my way up to this horizontal tangent, Okay, so in this case, x equals -2. Oops, sorry. What's going on over here as far as the behavior of the graph, the rate of change? It's increasing. So no matter what value I pick there, the result will always be what? Positive, right? So as we look over here, from -infinity to that -2, g prime of x will be greater than 0. At -2, it's equal to 0, right? That interval, we can say that. Where do I get that confidence from? Well, if you remember here, we can find the in behavior using limits. Okay. What you'll find is this is going to have a what we call a slant asymptote. So the ends of the graph will actually kind of tend towards this line here. All right. Well, if you follow that line, if we go to the left, it's going to go all the way to -infinity, right? So it's going to just keep on going following that line. Now, once I get to -2 and I go past this, well, the graph's going to just drop to -infinity, right? But how do we discuss that behavior from a derivative standpoint? Any rate of change I look at here it would always have a slope that's what? Decreasing or negative, right? So understand here what we see is from -2 to that -1, g prime of x is decreasing. Okay. Now remember, we can't use -1, so we definitely have to stop there. As we go over here, then from any point there, as we go towards this second turning point, the function's still decreasing. Would you agree with that? The problem is we just went going from -infinity all the way up to positive infinity, right? So there was kind of an extreme change that happens because of the asymptote. However, from a standpoint, we would include this with this whole decreasing. We'll say, hey, from -1 to 0, it's increasing. I mean, sorry, decreasing. Everyone follow me on that though? How I said increasing, but I put it with decreasing. Well, what happens over here then? Increasing, right? So that would mean that, hey, from that 0 to infinity, I can include that here. And what we're seeing is I can get all this information by just looking at that derivative. I didn't actually have to look at the graph. I can use the derivative to help kind of explain that. The graph was helpful here, right? But understand, like getting the graph on this previous function, you think that's going to be fun? No, right? I mean, we had 3 different turning points, right? And then we're gonna have to go talk about finding x-intercepts. This is gonna be a tedious one to have to deal with graph. The one yesterday on Wednesday, I mean, that was pretty straightforward, but I made sure that the graph was a little bit nicer based on the zeros I picked. Okay. Yeah, we had to use synthetic division to find them, but the graph I was more interested in, whereas here was just finding critical points. Okay. This one here was, hey, I felt like a great rational function to get to the critical points, right? But hopefully you see the graph helped us kind of see some of that behavior work in place too, okay? As you can see, this whole thing got messed up just now. All right. Was there any concerns or questions I clear up with that? I know the graph glitched out on me, sorry. That's what it looks like. Sorry, y'all. Was there any concerns though? Now, hopefully what you saw here, this is kind of where we're working towards is beginning to describe functions, knowing what intervals a function's increasing on from a rate of change standpoint or decreasing is definitely something that we've talked about, right? We've usually talked about specific points though, right? This is allow us now kind of have general discussion like, hey, we know from here to here, we're going to have an increase in our rate of change. But once we get to this point, there's a change that takes place to where now it's decreasing, okay? And so on. Now, here's another function I want us to work on. Okay, as far as the graph is concerned, oops, Who knows what the graph looks like because I just took two functions and put them together. Well, if we consider this one function and we consider this a different function, where did we see that we needed to subtract two functions to get something new? What was on some of the application problems we've worked on where we had to subtract two different functions? Right? Revenue minus our costs will give us what? Our profit functions, right? By the way, as we're sitting here thinking about that, if I asked you to find the average profit, what are you supposed to do to the profit function? Divide by X. If you buy a 24 pack of sodas and you pay $10 for that pack of sodas, how much does it cost per can? What would you have to do? That's all this is doing, right? A company's going to look at their sales. Like if you go to Coca-Cola, they're going to be saying, hey, not how much we put out per can. They might say, how much does it cost per ounce, right? And they might break it up depending on how it's bottled. But ultimately, how many ounces of Coke are we selling, right? As we look at this. So don't forget that the average profit function just means take the profit, divide by X. So if you ask to find average revenue, average cost, just divide by X because that's going to give us the average per whatever unit of measurement we're looking at, okay? Now, I just made this function up to kind of use both of those, okay? But if I give you this function and tell you to find critical points, what should we do? All right, let's go find the derivative. As far as this derivative is concerned, hopefully you'll see it's pretty straightforward, right? But what do we have to be careful of not to forget? Derivative of X is 1, the 25 goes to 0, so that's gone. The chain rule, right? This is one of those ones that we definitely want to be careful that, hey, when I deal with this, I need to multiply by 0.05 because that comes from the exponent or the chain rule of that, okay? Whenever dealing with exponential functions, make sure you watch out for that exponent. Because oftentimes, as we saw with some applications we looked at last week, that, hey, that K value is important to the derivative, okay? Everyone good with that?
Didn't understand how did we multiplied by 0.05.
All right, so remember the derivative of e to the x is e to the x, right? If you have e to the x with something other than just x, so we could just say u of x for generalization purposes, you'll have e to the u times du dx. Okay, where u, remember, is a function or something dealing with x. So understand here, since that was 0.5x, I need to multiply by the derivative of that. So that's where that's coming. So just make sure you see here, as we did with this here, like, hey, the derivative of negative 48x was just negative 48. It just so happens I made sure to use a, something that would represent percentages, right? So, hey, we've been doing with this, that would be like 5% K value.
The exponents for the E.
For the E, that's correct. But this is one of those things like, hey, anytime I have E to the X or any exponent, really, let me watch out for that chain rule. Okay. Watch out for radicals. I could easily come in here and say, hey, square root of X squared minus 3. Or if you're differentiating that, we need the chain rule. Okay. Does that help? Now, as far as this is concerned, if I want to find the critical points, what do we do with our derivative? So equal to 0, right? Now, before we go finish all this, do we have to worry about any restricted values in our function? Okay. So if we look at this piece here, That's just like a line, right? So that would be a linear function. Domains all real numbers. We're good there. Well, exponentials have a domain of all real numbers as well. So as far as restricted values, we don't need to worry about this here. Okay. The one question that would come in be cusp. Well, hey, we know like absolute values, that's one sign of a cusp. Brain's not working with piecewise functions. Watch out for cusp on piecewise functions. Okay. Here, we probably should be fine as far as a smooth turn is concerned. Okay. We'll look at the graph again in a second and just kind of trust that, hey, what we're dealing with will have some type of smooth turn because exponentials already have a smooth turn to them. All we did is just kind of added a linear element. Okay. With that said, this equation, are we going to get to a nice value for the answer? Should we expect a nice value here as far as our solution? No, right? There's an E involved, right? So what we should expect at some point is a natural log. Okay, definitely be watching for a natural log. So you can add the E to the 0.5x term to both sides. Okay. And then you'll end up dividing both sides by the 0.05 that's in front of it. Now, the nice thing about 0.05, that's 1 over 20. Okay. So what we'll really get here is 20 equal to E to the 0.05x. Now, anytime you have E involved and you need to get to that exponent, know that this is where our natural log is. So, hey, the natural log of 20 equals 0.05x. Okay. And we're gonna have to divide by 0.05 again. So that will just give us 20 times the natural log of 20 equal to x. Now, that is the exact value for our critical point. Okay. But if we're trying to graph this, we would definitely want an approximation. We'll say, hey, this is about 60. I got 59.91. Which, sorry. Yeah, whenever you divide by this 0.05, I just took the fact that, hey, that equals 20 and used it again. Yeah, so just make sure you see we had to do that twice. So that's why I didn't write it again. We did that here, and then we'll do that same thing here on both sides. Okay. So did we find any critical points? We found one critical point, right? What that means to me, if I go look at this graph, I should expect to see one behavior on one side and a different behavior on the other side. Not that that's guaranteed, but that's what we're wondering. This is what's going to bring us to the next steps. Okay. So is everyone comfortable with getting to that value, even though it's not nice? Now I'm going to use an approximation to 60 when we kind of look at the graph, but 20 natural log of 20 is the critical value that we're looking for. Now, in this case, when I say that, hey, there's a critical point and x equals to 20 times the natural log of 20, what am I declaring is happening there for this particular function? Horizontal tangent. So when we see this, we're saying that, hey, at this value, the derivative is 0. We just did all that work to get that, right? So we know at this value that derivative is equal to 0. Okay. Now, we're not going to stop with just identifying critical points. What you're going to see is we actually really want to go into something I'll just call the first derivative test. Okay, we're going to use the first derivative in these critical points to help describe the function. Okay, now you'll see I kind of walked through it just now with that rational function. And I gave us intervals of increasing and decreasing. That's really what we're trying to get to is where is my function increasing? Where is it decreasing? Okay. So what we want to do is just do a quick little number line here. On this number line, what number should we focus on? Now I'm going to keep it as the natural log of, or sorry, 20 times natural log of 20, but we're looking at, hey, it's pretty close to 60, right? That's what we're focused on. With that said, this kind of will remind you of whenever you were solving inequalities, right? So if you're trying to find if something was greater than less than, but what we want to do is describe everything. So what we're going to do is go pick a value over here and then another value over here just to kind of test what's going on. Now, having that understanding this is about 60, what's a number smaller than 60 that would be easy to plug in? You could definitely do 50. I would encourage you to use 0. Okay, you don't have to, you can use 50, that's perfectly fine, okay? What's a number greater than 60 that someone would like to use? Let's use 100, that, okay? Now, the key is we see with inequalities back in college algebra, I could have picked any value on the interval, as long as it was less than the number or greater than the number, it'll match the interval we're working on, okay? Now, with that said, what we want to do then is say, hey, let's take these values and plug them in to our derivative function. Okay. So as far as the derivative function is concerned, make sure you remember that was the 1 minus 0.05 e to the 0.05 x. Okay. So first things first, let's go find the derivative when it's 0. Well, hey, the nice thing about picking 0 here, the exponential goes to 1. So we'll have 0.95. Okay. What do I expect you to use to find these values though? What should we be using to plug these things in? A calculator. Please make sure you're doing that. Now, the 0 was nice because e to the 0 is 1, right? So 1 minus 0.05. Well, 100 minus 5 is 95. Okay. Now, as far as the derivative at 100, plugging that into our calculator now, negative 6.42. Rounded, of course. What do I want to take from this, though? All right. One of them's negative, right? What we just found is it didn't matter what number I pick over here, what's always going to be the sign? Well, hey, my derivative is always going to be negative. It is less than 0. No matter what number I picked over there on that interval, the derivative would have been a negative number. If you don't believe me, go plug in 200. We calculate for 200. It gives us negative 11,000 approximately. 1,100, sorry. It's about that, right? If you plug in 61, we get all the way up against this. I plug in 61, it gives me about negative 0.05. I'm just roughly estimating, but make sure you see here, they're all negative. Doesn't matter where I pick. So always pick numbers that are easy to plug in. Okay. If you plug in that 50, what should I expect? Type of number should we expect from 50, y'all? Positive, right? So if you chose to do 50 instead of 0, it's going to work just fine. Okay, so please understand that. Doesn't matter what number it is, just make sure it's either greater than or less than the critical point you're working with. Now, things to be careful of, as you saw with my graph that we looked at, it was -2, -1, and 0. They were pretty close together, so you're going to be forced to use decimals sometimes, okay? Or fractions, however you prefer to deal with it. Now, over here, though, what we see is that all these values are going to be positive. So if we were looking at the behavior of the function, what would you tell me is going on the interval of negative infinity up to the 20 times the natural log of 20. What is that interval doing here? As far as the behavior of the function, is it increasing, decreasing, or constant?
Decrease.
It's increasing, right? We know that because the derivative is positive. All over here, right? That's no matter what value I plug in, my derivative will always be positive, okay? Now you'll find, when we look at the graph, you'll find it pretty interesting how these two kind of play close to one another, okay? Because what you'll see is when we get to the left of this critical point, the linear function is kind of a little bit more influential on its behavior. But after we get past this value, the exponential function is more influential on its behavior, okay? Because what number is 0.95 really close to?
One.
It's 1. Well, what's the slope of the linear?
One.
1, right? Now, we wouldn't necessarily deal with negatives all the time, but go plug in something like negative 100 just to see, right? I got 0.9997. From a limit standpoint, right, what we could take from that is we're never actually probably going to get to 1 when the rate of change that is, right? The rate of change will never actually get to 1, but we could say it's approaching 1. Okay, does everyone kind of see that? With that said, though, this was just one aspect, right? This was just one side. This goes with what we found over here. Okay. So what would we say about this interval? It's decreasing, right? Now we don't need this anymore, so let's get this out of the way. So I'm going to drag this over to say that, hey, once we get to this 20 times natural log of 20, as we go to positive infinity, j of x is going to be decreasing. And we're getting this from the first derivative, right? The average rate, the instantaneous rate of change at any point would be negative. Okay, this is what we call the first derivative test. With that said, if one side is increasing, one side's decreasing, what's special going on at this particular point? What is the graph doing? The graph is turning, okay? Because the graph is turning, that point's going to stand out. With that said, is there any value on this graph ever going to be above that value? It's going to continue to increase up to this and then decrease the rest of the way, right? So what's another special thing about that point? It's a horizontal tangent, right? It's a turning point. When you consider and compare it to every other point on our function, this point is where when compared to those. I wouldn't necessarily call it the middle here. If we were talking about a quadratic, though, when we consider a vertex of a quadratic, right, that is technically we can make justifications for the middle of the graph, right, the axis of symmetry and stuff like that. But on the graph I did up here, if we just kind of compare it to a quadratic real quick, this would be a horizontal tangent as we looked at, right? That's why we call the vertex special. One side will be increasing, one side's decreasing, but that point is where, when we consider to all the other solutions on this graph, it's the maximum. It's the highest point possible, and it's going to be what we would actually call the absolute maximum of the graph, right? Nothing else is higher than it. So this is where the first derivative can help us a lot. Describing stuff as far as increasing and decreasing, but whenever you have a change from increasing or decreasing, you're going to have a turning point that represents a relative minimum or maximum. Okay. So here we would say, hey, there's a relative max occurring at this value. Okay. Now let's go look at the graph though, so we see what that looks like. Does everyone go with this slide though before I do a quick sketch of the graph? Well, don't do that to me. All right. So as far as this line is concerned, what do we notice about it? Okay, make sure you see here, if we go focus on that point that was highlighted right here, that was be the point we found just now. Okay, I know you can't, can I make the text bigger? It didn't help. What you'll see there, it says 59.91, which is basically what we just said, 20 times the natural log of 20 is about 60, okay? With that said, though, everything to the left of that point, it's going up towards that, right? So we have an increasing slope, but what pattern, if I cover up the whole right side here, what graph does that look like? It looks like the line, right? It almost kind of looks like X plus 25. Now, it's not X plus 25 because we know that, but if we didn't know the rest of this was going on, we wouldn't be able to see that. But guess what? We went and found this point to realize that, hey, as we consider this function, after we get to the about 60, it begins to decrease. And you'll see there that kind of follows more of like an exponential decrease, right? Because it's dropping so quickly. Okay. Now, because there was a change, we'll call that a relative max. Okay. In order to say that that is the absolute highest point, that's where we would need our limits to infinity. Okay, so what you'll see here is like we would have to go talk about the limit as x goes to negative infinity of j, the limit as x goes to positive infinity of j of x, which, hey, based on the graph, we should see that both those are negative infinity, and then that's the absolute max of the graph because of that. Okay, so that's going to be something that we jump into now that we have this in place. Okay. The other thing I will say here is remember the second derivative is also part of this conversation. Okay. What you'll find though, as we jump forward into the second derivative, that's where we're going to talk about that concavity that we discussed on Wednesday. Okay. So understand the first derivative test is going to be for function behavior as far as increasing and decreasing and help us find relative min or maximum. Relative extremum is what we'll call it. Okay. For this graph, as we look at the graph again, if it goes from increasing to decreasing, it's like climbing a mountain and then going down. So that would tell us like, hey, I have a relative max involved, okay? Everyone kind of see how that plays out with the function that I made up for this instance to see the behavior. Some not something we would have recognized right away, but hey, how can we see that play into the function? Any questions or concerns with that? All right, well, that's where we're going to stop today. I hope that helps you as far as seeing that.